we'll switch to English. We have a few students. So welcome everybody. It's a great honor for us today to host Professor Baras for a talk, and a very interesting talk. John Baras is a distinguished university professor holding the Lockheed Martin Chair in the Systems Engineering in the Institute for Systems Research and the ACE Department of the University of Maryland College Park. He graduated from the National Technical University of Athens back in 1970, and then he moved to US where he received his PhD degree in applied mathematics from Harvard University in 1973. Since then, he has been with the University of Maryland College. From 1985 to 1991, he was the founding director of the Institute of Systems Research, and since 1992, has been the director of the Maryland Center for Hybrid Networks, which he co-founded. He's a life fellow of IEEE, and a fellow of SIAM, AAS, NIA, IFAC, and many other American institutes. He has many major honors and awards, and I will just pick up a few of them. In 2016, he was inducted in the University of Maryland J. Clark School of Engineering Innovation Hall of Fame. In June 2018, he was awarded a doctorate honoris causa by his alma mater, University, National Technical University of Athens. And his research interests include systems, control, optimization, autonomy, and the list goes on. So thank you, Professor Baras, for being here. And the title of his talk will be Autonomous Vehicles Planning, Control, and Safety in Mixed Traffic Environments. So thank you very much. The floor is yours.
Can you hear me?
Sure.
Yes, perfect. Otherwise, I have to use the microphone. Hopefully. The microphone is next to you, wireless. Okay. So I'm very happy to be here again. I was here last when Dixie Drop was my ex-student, was chair of the electrical engineering department. I was pre-COVID. And I've been here several times even before that. So I wear my glasses because my vision is not as good as it used to be. So I have a strange property that one of my eyes sees far and the other sees short. And because it happened gradually, the doctor says that the brain has been able to adapt. But okay, so I want to talk to you about work we are doing on. We do a lot of work in the subject of trusted autonomy. Because, I mean, basically we are very strong about this, and we say, you should not talk about autonomy without saying trusted autonomy. It means that the autonomous system must have the ability to monitor the execution of tasks, to be able to detect if the execution is not done well, adjust and learn in the process. And if you think for a minute, this is very natural, and it's actually, that's how you do it, because you try to figure out how you do it, how you drive it, and so on and so forth, and try to correct it, and so on and so forth. So autonomous vehicle is a prime example of this. Okay? And one other aspect of autonomy that we are looking at more and more so is the issue of robustness. I have decision making, but what happens if I have things I cannot, I didn't plan for, like I'm driving the car and all of a sudden I'm going on a mud, or it's raining. How can I adjust to this thing? Okay? And we work with companies in some of these problems, notably with the Fonda Research Institute. The second part of the talk is that. The first part is a lot of work we did with Nokia Labs, okay, who are also interested in the software side of the problem. Okay, so this is the work primarily of two PhD students, Naila Suriyarasi, who is now at Nokia Labs, and Faisal Tariq, who is actually with the Fonda Research Institute in Silicon Valley. This is Mavridis, who is a PhD student of mine, he's now at KTH. He worked with me on machine learning and AI, and at Rani we did the talk we did the work where we unified many issues of robustness in machine learning and in AI and reinforcement learning by using the theory that we borrowed from mathematics of finance, where we have rigorous Legendre duality between performance and risk. We have been able to show that many of the properties that we want, like safety, reliability, and other things, can be monotone functions to some sort of risk. And risk is very important because, thanks to the so-called prospect theory, 2 Nobel Prize winners did examination of experimental data to decide how humans decide. And that showed that the old theory of von Neumann, which said that humans decide on the basis of some maximization of expected utility, is not correct. Humans actually balance the expected utility with the risk. And one aspect of the risk is volatility or variance. Okay? So for instance, and why it came from mathematics of finance is obvious, because if you are investing in finance, you want to understand what is the expected gain of your investment, but also you worry about volatility, which is risk. If the volatility is high, you have to be careful because you may gain a lot or you may lose a lot. And there are examples of this in many engineering. You will see an example of that in the problem of going on the highway and trying to guess how aggressive or non-aggressive are the drivers around you, and then adjust the tolerance you leave so that if they do this, you are prepared for that. Okay? That's where we use these ideas. So, the first part of the talk is a problem about connected autonomous vehicles. Okay, now we have vehicles that can communicate between themselves or they communicate with the infrastructure. And with NILS, we studied this, what can do these problems, and there are several set of problems here. Alright, so you all have seen this data about how many people had accidents in the US and so on and so forth. So safety is of paramount importance here. And you can see the different cities with all these accidents. And safety is of paramount importance in autonomous vehicles. But unfortunately, the problem is not autonomous vehicles. And the reason we don't see autonomous vehicles in the street right now is because human people. Okay? So it's the human drivers, because they have very unexpected behavior and so on and so forth. That is the problem why we don't see autonomous vehicles more in the streets, and why all the promises that people have made keep postponed. Okay? This is what we mean by mixed traffic. Okay? Mixed traffic is partly autonomous, partly human driven. Okay? And there are positive and negative things of this. But if I look at connected autonomous vehicles, first of all, they can help each other. So there's a famous example where I'm going on the street like that, and there's a car here that is damaged, and if I don't get information that there is something problematic here, I may go crash. That's an example, for instance, that Qualcomm uses, because Qualcomm has this chipset that's called Snapdragon, and they try to make this a primary provider of chips for autonomous vehicles for this kind of problems. Okay? Not so much for running the engine, but to actually make the vehicle to be an intelligent agent within the environment. You have improved computation, you have extended communication, benefits of safety, because they can collaborate for the safety of the vehicles, communicating between themselves and the environment. I was actually in the late 80s in 2 labs in Japan, in Honda and another company, and they showed me this collaboration between vehicles and motorbikes in terms of safety, like if there is a bump somewhere, which may be dangerous, they will inform each other to try to change the path and so forth. We're talking about almost 30 years ago. There's a lot of improvement there. And so the talk that I'm going to give you here, this first part, is multiple collaborative autonomous vehicles, improved efficiency at the global level, and also some positive use of these vehicles to try to ameliorate congestion, okay? Which is related to shock waves and so on and so forth. Right, so let's go through them. So the challenges is what kind of control you're going to get. Are you going to get centralized or decentralized? When you have heterogeneous vehicles, what happens? What do you do in mixed traffic? What is the timing performance of the algorithm? Because they have to be fast, right? In milliseconds in a car, you travel meters, you hit each other. And then you can see here the effect of communications. This is a topic that many companies in the US are interested in, including General Motors. How much do I gain from vehicle-to-vehicle communication versus not having it? How much do I gain from vehicle-to-infrastructure communication? And even between satellites and vehicles. Of course, the time scales are different. The vehicle-to-vehicle are very fast communication, the vehicle-to-infrastructure slower, the vehicle-satellite slower. You only use a vehicle-satellite, okay, when you go to your Google Maps and try to get information whether the path that you chose is congested or not. You see the red, yellow, and so on and so forth, and quite often you get upset because there's delay in the information, so the information is not recent. And you go to somewhere where the traffic, the Google tells you it's red and it isn't red, and so on and so forth. So there are issues there. Okay, so the first problem is cooperative highway merging. Okay? The problem is I have a highway here, and there's another, and I'm trying to make them to go peacefully without hitting each other. Google itself has a pattern to this, okay, where they actually use orthogonal parallel paths for the models of the truck or the cars. The difficulty is try to do the reasonable thing, like one car passes and another one, and so on and so forth, which many drivers in many countries, I won't mention, they don't obey it. They try to compete all the time and they create accidents. Okay? And the difficulty is that the size of the cars are not the same. You may have a truck, you may have a small car, and so on and so forth, and you have to have a lot of interesting scheduling and cooperation between the vehicles to do that. This is what we did with ILS. So you have centralized control, right? So you have you have the vehicles. Let's say that their dynamics are described by this nonlinear equation. This is some noise and disturbance, and your control is the velocity. You try to accelerate or decelerate, okay? And then what brake or go faster, and then for each vehicle you have some variable that gives you an index for the priority of the vehicle and so on and so forth. And then another variable, this is between 0 and 1, this is 0 or 1, and therefore you have the scale, the full model of the vehicle is a hybrid system, essentially, because you have some of the states that are continuous, some of them that are binary. Okay? And then you have various bounds on the velocities, and because you have speed limits, okay, and remember if you go to a turn, they tell you not to go very fast and so on. So we've taken care of all that.
But all vehicles are automatic, right?
Yeah. No, this has nothing to do with the human. This is the second part of the talk I will talk about here. So you try to maximize throughput, and you try to minimize control effort, and then you compute the optimal velocity, and select this merging sequence, like the queue tells you who goes, okay, who doesn't go. Okay. So there are two problems in the scheduling, in the control problem. Select the velocities and select the sequencing. Okay, so there's quite a lot of work here. I don't know if you can see it, but you will get the talk. So Malkopoulos has done a lot of work here. There are other people like Ding and so on and so forth, and Marinescu and so on and so forth on these things. So there are various analytical solutions, which are closed-form solutions to centralized problem. You have even AI, old-fashioned AI, rule-based systems, and then slot-based allocation method. Okay, so what a slot means, I have a virtual space in the highway, which I put a vehicle in, or I have an empty spot, and then I allocate spots to vehicles. Okay? So this is also happened in something that's called intelligent highway systems, in which the late Praveen Varaya was a pioneer, where you have spaces in the highway, right? And then you allocate vehicles, and then you go automatic. So this becomes like a train, except the train is virtual, because the vehicles between themselves keep the distances, and it's like a railway going, and you just allocate the spots according to the size of the vehicle. Okay, that's the course of the intelligent highway. Let's come back now, because we believe, at least in the US, that the first time you're going to see fully autonomous vehicles, regardless of whether you have drivers or not, it's going to be the highway. I go to the highway and then I go to sleep, and it takes me from Washington to New York this way. Okay, and then I take over again. Right. And so many of these optimization solutions, they're not fast enough. That's one problem. The rule-based attempts, as we all know, the old-fashioned AI and the rule-based attempts, they are not behaving well when you see something that you didn't expect. So they are not robust. And they don't, if you try to handle heterogeneous traffic, it becomes very complex, because you have to know different categories of vehicles, and you have to have much more complicated controls and so on and so forth. And that's the last bullet, that you cannot handle easily mixed. So what we propose is this sort of pipeline in this paper that you can get. It's called the best paper award in this conference. So you have the information collection, you have the priority assignment, the sequence generation, meaning who goes, okay? Then you have the optimal velocity optimization for different vehicles with different criteria. You have an environmental simulation. We have not done that in the real traffic. We use very well-known simulators to do this validation. And then out of that, you get the optimal sequences, like who goes and with what velocity. And then you have different kinds of level controllers, low-level controllers, and you try them and you see what happens. We compared actually these algorithms with the algorithms that you get if you apply the Google pattern, okay? And they perform better, at least in simulation, okay? I'm not going to claim that. But I'm telling you the Google pattern not because I want to tell you that they're better than Google, just to tell you the problem is important enough for Google to spend the time to study it and file for a patent for the algorithm they have, okay? So, if I have got a heterogeneous traffic, you have now a more complicated problem because you have to assign priority indices to different vehicle types. For instance, you have an ambulance. It has to go through faster, okay? You have on-ramp or mainline vehicle, you have current speed, vehicle feature intent, waiting time, and so on and so forth, okay? The emphasis here is to try to get, first of all, if the traffic is low, everything is easy. The problem that you need to study is when the traffic is not low, but there's a lot of traffic, and you have to decide now how to make space for all these things and so on, in a way that is smooth and works well. So you have different priorities. One is speed prioritization and speed variation prioritization. Okay? I'm allowing you to have faster speed or slower, or I'm also allowing you to stay on the speed more than others. And then you consider flow over effect for high priority vehicles in the back of the queue. Right? And here is the optimal merging that we've formulated. If you look at the problem, it doesn't take time to realize that because you have continuous variables and Boolean variables, you're going to end up with a mixed integer programming problem, which is actually bad news, because most of the mixed integer programming problems, they're pick-of-pick. So if you want to run them fast, you have to come up with some good heuristics. There are programs like European and Simplex and others that they have algorithms that you have to sometimes do even more to try to get them to the performance. And we'll talk about this in a subsequent slide. So you solve this by generating a merging sequence, and then you compute the optimum velocity commands to achieve the merging sequence. Okay? So I decide with finite horizon what is the merging sequence, and once I know the sequence, I optimize and find the velocity that I need to have to be able to achieve the merging sequence. Okay? So the number of sequences is a problem. It's combinatorial, it's huge. Okay? So if I have n equals 30 and these variables here, you get an astronomical number of sequences. Okay? So again, you have to do something to be able to do that fast enough. So the sequence generation method we have is, if we look at the rule-based method to select the sequences Q, we do it by a sorting algorithm, which uses as input the distance to merge, how far away I am from this flow to go to the highway, right? The time to merge, which in robotics sometimes we call the time to crash. Okay? You do motor predictive control, like you see in the car. You see the tube where you're going to go, and you also calculate the time dependency. And if they don't agree, you have to do something. Okay? It's similar to that here. You have waiting time. Sometimes you go to an intersection, especially with the signalized access to the highway, as you have in California. You may create a queue, and the queue creates delay. Okay, there's a problem. And then you have vehicle priority. So we combine these criteria by various kinds of weights, like you see here. Right? This is the time to merge. Okay, this is the distance. This is the priorities that we have. And the variables that we have here, the weights, as usual, are numbers between 0 and 1. Okay, so what are these? Okay, the problem here, because you have many criteria, it's a trade-off problem. And to try to solve a trade-off problem, there's an optimal solution because you have more than one criteria, right? So to give you an idea, if you have two criteria, I'm going to do this way for you, and you try to minimize this and minimize this, okay? So you want to be down here somewhere. All right, so one way to do it is you take and put a bound on this metric, and you minimize the other one. You find one Pareto point that will point, and you take more. And that's not going to be fast, because you solve many optimization problems. what you see here is what's called scalarization method of trade-off analysis, where you combine the metrics by some convex combination of variables, like you take lambda f1 plus 1 and lambda f2, you solve one optimization problem. Of course, the question is who gives you the lambda? And the same thing here, who gives you the alphas? And this can be something that you can actually do by learning, okay? Or by other things, like logical priorities. I want to give certain variables, okay, priority, and then you adjust the weight, okay? So this is the underlying mathematics here. Pareto's theorem tells you that if the trade-off curve is like this, if you do the scalarization method, you compute the tangent, and the coordinates of the normal vector are these weights, okay? All right, so this, of course, will miss if the trade-off curve is not convex, but who cares? You're the designer, and if you have any interest in mind, you're not going to choose a metric that is not convex, because that makes your design problem more difficult. So one of the things I emphasize in these talks is that the designer is in control of how you represent the constraints. So you don't make your life more difficult than it has to be by picking things that they are difficult to compute, because in many of these applications you have to compute fast. And the other point I want to make is constraints and metrics are dual concepts. If I want to turn a constraint to a metric, I put a barrier function like this, and then minimizing this function is the same as keeping something between two bounds. If on the other hand, I want to treat a function that I have to represent my constraint, like maximize or minimize, I do look at the level sets. Again, because you are the designer, you choose how you represent your specifications that are given to you verbally, how you mathematize them. You can do them either as constraints or metrics. It's your code, okay? And you choose the one that you think, or you can solve by experimentation that you can do fast enough. Because in these problems, you have to solve this problem fast enough. Okay? So you generate a range of sequences by varying the alpha, beta, gamma, and then you get more sequences you get to higher performance, but you have to be careful here because then it gets slower, because you have to examine more options. And then, as we say here, if you test additional sequences, you increase the computational load, so there's a trade-off between the number of sequences and the computational power you have, and more important, the time it takes to decide. Okay? It's the same thing as looking for vocabulary, and if you're looking for a lot of vocabulary to find not the vocabulary, but a catalog of responses, you drive it, and somebody walks in front of you. You don't have the time to optimize. You have to have a catalog of responses. You pick the one that is reasonable because you have to act quickly, okay? In the fast scale. Same problem here. Right, so we did this. In terms of computing the optimal velocity, once you have the sequencing, it's simple, again, same combination of these metrics, but it's a quadratic criteria. So that's why the overall problem becomes a quadratic mixing is a programming problem. And then you have very efficient algorithms to do that. So you maximize the throughput velocity and minimize the control effort, right? That's fuel consumption. This is reflected here in these weights. And then, as I said before, the lambda provides a trade-off between these, okay? So individual priorities allow each CAV, each autonomous vehicle, or collaborate if you like, to decide its own bias in any of these criteria. The problem is mixing this programming quadratic, and I can solve this by incorporating the variable BI into the priority BI and test the sequences and restructuring the constraints if you don't have what happened. So it's not very complex, and you can then have constraints on the optimal velocity. Okay, so I have another bound, the speed limit. Okay, or I can take the acceleration probability of the vehicle like I have here. Okay, how much I can accelerate or decelerate with this. The variable that we saw before, AI minimum and AI all these things. Okay, then you have area collisions, how far I can come close to you, which many of the vehicles now have autonomous controls for that. If you have these modern vehicles, you can change lane, right? If there's nothing in front of you, you accelerate. If the motorbike comes suddenly in front of you, you immediately see because it tries to keep the distance, okay? And the problem with many of the controls we have in autonomous vehicles today is they are not well integrated. So in experiments we did with General Motors, you may have a lane following and a distance following, and you have two cars. So I take them to go to a very curved street, accelerate a lot, and this car goes off. Because they have never been system engineered to integrate the controls so that together, jointly, they work well. Okay? And even a small delay in the coordination creates this problem. Okay? So, I'm telling you that because there are famous examples in experiments and DARPA challenges and others where you have a lot of sensors and actuators in a vehicle, and then the vehicle may see an environment that you expect to work well, and it doesn't because there has not been integration between the sensors and controls in the systems engineering frame. In other words, there has not been a joint integration of these things. Lateral collisions in merging zone are avoided by this constraint. Okay? And this ensures that the merging order of sequence Q is followed. Okay? So if you look at all these parameters that are introduced, there's the velocity, there's the timing, and there's a constant here that gives you the bound that you want. Right. So if you have human-driven vehicles, you have all kinds of constraints. Okay, so you have a predicted velocity from whatever you observe of the vehicle. You have a lead vehicle speed and the gap to the lead vehicle, that's the variable delta you see here. You have the speed limits on the highway and the parameters eta you see here and tau, right? They model the human driving perfections and reaction time. So are you fast or you are slow? What kind of driver are you? To the extent we can. Of course, we understand that it's very difficult to model humans, and you hear this again and again. Okay? So for every collision checking constraint, right, we pay the pairing of a human-driven and an autonomous vehicle. So you increase the safety margin. You implement increased safety margins and you account for the prediction error in the human-driven. Okay, so the problem with the human-driven is you have higher uncertainty. So if it's all autonomous, as I answered before the question, then it's easy. It's more difficult if you have partly autonomous vehicles and partly human car that they try to merge that. And the problem is the uncertainty of the humans. In the autonomous human car, you don't have enough sense. You designed it, and you can have bounds in uncertainty, but you know them. In the humans, you don't. Okay, and this is something that we try to address. So the optimal selection of the sequences is you run the optimization for each sequence in parallel. That's one of the things we did. You obtain the sequence for which the minimum objective value is achieved, and then you provide the command vehicles with the velocities, okay? And we assume that you have zero communication delay between the vehicle to infrastructure, okay? Which again is not very realistic, right? Because, but in short distances, if the communication is on the side of the street, for instance, instead of Maryland, we have very well instrumented highway, so this is not so bad. But the flow path is the same, as I explained before. And this allows merge sequence to be changed at every update cycle. So think of it as running it over a finite horizon, and then you update depending because things may change. So this is like, it should remind you receding horizon control, except now I don't overlap them too much. So one way to go from a long interval to a short interval is you do the same algorithm but shorter interval. So it's better run faster, right, than in a short interval, because you need to adjust it very frequently. So that's the problem. And they've been able to do that.
Sorry, John, the Google patent is for all vehicles being automatic or also some?
No, this includes also human drivers.
No, this yes, but you talked about the Google patent.
The Google is only for autonomous.
Only automatic.
Yeah, that's a very good point. Thank you. So, one of the things we think we did, I don't see many papers on that, you try to do the problem when you have multiple lanes on the highway. Because this allows people, they come this way, to go to the next lane if there's room, right? And then they give you more room to enter into the highway, okay? So this adds an additional parameters and variables. And then you have to have lane changing controllers that they work well. And then the lane controllers operate in parallel with the central major controllers and identify when lane changes are needed. And so in other words, I have the centralized controller of this merging, and I also try to figure out what's happening with the lanes, and if there is room for the change, I tell the car or I tell the driver change, because I want to make room for that. Okay? This is very useful, particularly if you have emergency vehicles, because this way, and you've been like that, the police or the ambulance comes on, puts the CIA and everything, and people don't move. Now, if they don't have space to move, fine, but sometimes they have move and they can freeze. Okay? That may cause minutes of delay, which can be fatal. Okay, so anyway, let's see what happens here. Oh, the movie doesn't play. Oh, no. Yeah. So you can see the movie here that works. This basically, we use simulation, okay? Sumo simulation and qubit optimization. So it works, and then you can see several different parameters here. You can see the throughput, the comparison, okay, between various forms of solution, okay, and ours. And then you see here the density comparison as you increase traffic, okay, that we still maintain the reasonably good thing. And then here is about the delay, based computation. So if you use some of the other methods, this goes really bad. And then you see fewer comparison. Again, we are doing well. Our argument is one of these two, either the green or the blue.
Do you reach critical density?
Sorry?
Do you reach the level of critical density? Or?
Yeah. So you get things like, if I go to higher density levels where you have more traffic, these algorithms give you better improvement. In other words, they work better in difficult situations, because if the situation is easy, almost anything will work okay. And that's what it says. We have 83% improvement in delay phase, 50% improvement in density, 30% improvement in fuel consumption, and so on. There is detailed papers, and even the thesis of Niles, if you are interested, but the papers have the results, and they are here listed. And you will see in the end my email and my webpage, and you can get me to give you whatever you need. Okay. Then, come back to the question. Your question, Marcos, is we also looked at what happens as you increase the percentage of autonomous vehicles versus human driven, okay, which is an important question, because people think that because I control better the autonomous vehicles, I can help them to control better the traffic. And that will show in different circumstances, including here, that you get the performance at higher CAV penetration levels, because you have more control of the traffic, because you control completely the autonomous vehicles, but you don't control the humans. But you can use them. For instance, you can go put an autonomous vehicle in front of the traffic and it has to slow unless he wants to hit you, which he's not going to do, okay? Or see. To be careful there, okay? And then at the CAV penetration levels of 80 versus 60%, 100 versus 6%, you get 10 to 19% improvement in throughput and 25 to 50% improvement in delay phase respectively. You use the autonomous vehicles to control the mixed traffic. These are your agents of slowing down things or getting better service. So, now about the timing, okay, we run this into the update frequency is about 10 Hz every 100 milliseconds. If you do in parallel computers, you get 50 milliseconds on 12-core CPU, and you can do real-time operation with the margin of error included, and this is feasible to run in a not so expensive computer on the car. One of the issues that we have to face with autonomous cars, how many of you have seen that, is when you get these crazy sensors that go at the top and they get in videos 360 degrees. And we went to the labs of Qualcomm, and you can see that, and I asked the person, what do you do with it? He says, I'm storing them. So he opens the luggage compartment of the car, it's full of drives, right? Full. You cannot put any luggage, storing the data. Okay, fine. And then I asked the question, how much of the data you actually use in the algorithm? And the answer was less than 1%. And then you ask, why? And the reason is that if you don't do that, they don't give you a license to do experiments on the street, the insurance companies. I'm telling you that to understand that it's not just a technology problem, right? It's a problem whether the humans will, the public will accept autonomous cars, whether the regulatory people and the politicians will accept it. It's a much more complicated problem than creating the autonomy. And that's one example of that. And that's not the first time we ran this. We ran this with medical technology and so on. Let me know about it. Then you have the centralized formulation of the problem. This was centralized. So now I'm going to group the vehicles and try to control the groups, which is faster. So I have a two-level control. I control the groups, and then within the priority, I control inside the group. So how do you group them? As you see here, okay, you see I group across both the highway and the flow that comes in. So I can do it based on connectivity. I can do it by computational power. I can prevent too many overlapping groups and so on and so forth. It's a clustering problem. So when you have a clustering problem, you have to have some measure of how you cluster, but then the question is on what would you cluster?
So the groups merge all together?
Yeah. Or you do the merging within that group. Like in this here, you will tell me how this three will merge.
The group comprises both
It depends.
Mainstream.
The operation is a very good one. Here, I do this. Here I have two groups, right? So now I have to see how the two groups do that, and then within that I see what the individual do. So it happens that sometimes the group is across the highway and the flow, and then I do just a measure for 3 or 5 years. Or sometimes I have two groups and I have to do the measure of the groups first and then the individual. Okay? We did this because it runs faster. Okay? As I say, so this reduces tremendously the number of sequences, meaning who goes and who doesn't go. And look, when you drive, you don't look at the entire highway. Okay? You look at a few cars in front, and you're supposed to be both reasonable and follow the unwritten rule that one goes and another goes. Okay? But if it doesn't happen, at least you don't want to wait forever and block everybody. Okay? So that's the idea. I reduce the number of sequences a lot if I do that, and then you combine the groups as a result to complete. And then when, like we have here, you have vehicles belong to multiple overlapping groups, like you see here, right? Then you choose a strategy resulting in lower cost. Here, right? This vehicle depends on this group and on this group. This vehicle depends on this group and this group. Okay, so you have to choose what you're going to do. How you do the local control. Alright, so that's one problem. The second problem, you all have seen these pictures that we don't need traffic lights anymore. Okay? And they go like this, and then you go to India and they start throwing, various animals on the intersections and bicycles and so on. We have a very good person in our university by the name of Professor Manosa who looks at this difficult problem. So how do you do intersections where there's all kinds of traffic flow? Here is just cars, different kinds of cars and buses, but there's no traffic intersection. Right? That's why it's called unsignalized. So we did this by actually a problem of using something that's called auction. Auction is you bid. I want to have performance. This happens a lot in communication network, right? I bid to get the bandwidth. And then very quickly you decide what to do. Here is the same thing. I bid to go first over here, and then you follow. So it's a combination of auction methods and optimization. You can see here, for instance, you have this traffic, and you need to know the intent, right? So I need to tell everybody that I'm trying to go right, or I don't have any lights, and then everybody assumes I want to go straight. It's very important to understand that. Many drivers don't understand the significance of giving directional lights. In France, if you don't use the directional lights, you get the ticket, right? Here, sometimes the person starts the ramp, the same thing in the US, and then turns the light, which is useless, because I don't have the signaling. I don't know what your intent is. So for me, this is a big uncertainty, because all of a sudden you found you intend the light. It doesn't happen. So for this to work, you have to have this, right? So you have the approach is over here, you have the inputs and the directions, then I generate the optimal sequence. Again, who goes to where, okay? Who has to wait. Sometimes when you have a traffic light, okay, it goes periodically. First goes straight, then people go right, and the other, so it goes like this, okay? So here you don't have that. But you have to decide, therefore, who you're going to give the right to do what their intent is, to turn or left and so on. And this depends on the traffic that you have completely. Then you compute the optimal velocity again, and then...
So you have pre-specified paths in the crossing area.
I know where I have to go, yeah.
Yes, you know where you want to go, but also the path you go there.
Yeah. Okay. Otherwise, I cannot adjust. You suddenly decide instead of turning to straight right, we're going to have a problem. And the problem is going to be, I'm going to stop, because I don't want to hit anybody. That's overrated. Anyway, so that's how it moves. Okay, so I do the optimal sequences. Then that tells you. Okay, in many of these problems, it's important to understand. You first describe what you're going to do in words, then you mathematize it. If you don't mathematize it, you don't have algorithms. All right. If you mathematize it and you do algorithms, then you can get performance easier. If you don't mathematize it, you get algorithms that are typically ad hoc, and it's much more difficult to estimate the performance of the ad hoc algorithm because you don't have mathematical support. Right? It's not that you cannot do it, it's just more difficult. I want people to understand that. To evaluate rigorously and validate performance of ad hoc algorithms is more difficult than algorithms who really have a mathematical theory. Right? Because if I know I have value optimization or gradient, I have ways to understand this. If you're doing something ad hoc which may work well, you have to get bounds of performance, and this is not easy. All right. And I don't buy a proof of performance just by simulation, because you can never simulate all the possible scenarios and all the things you want. Okay? All right. So, so you have guaranteed safety, efficiency, and fairness. We want to have, these are the criteria, right? I want to have less than 10 milliseconds. I need to have dynamic and balanced traffic management, and I want to have multi-lane conflict resolution. If I have many people that want to go straight, I'm assuming that you're not going to go from the left lane all of a sudden go right, okay? Because then we're going to have a problem, because what are these people going to do? Okay, so anyway, so you want to have increased throughput, reduced time spent, and reduced fuel consumption. Okay, these are the algorithms. And the algorithm we came up is called game opt, right? So you can put again the priority. Again, you get multiple bids in the auction, right? Then how the vehicle bids is you get distance to intersection, time to intersection, waiting time, driver preference, bidding capacity based on vehicle class. And then you do this sponsor sets auction, and then you get multiple sequences by changing the weights, as I showed you before, and then once you do that pretty fast, you compute the optimal velocity, and then you go. And again, you change this over short periods of time because the situation changes. Okay? Right. So that's the idea. If you have, so this is a multi-lane intersection design, as you can see here, right? So you have autonomous vehicles and non-autonomous vehicles, and these are noted here, like when you see CAV that's collaborative autonomous vehicles, the others are not autonomous. So you have various groups, 0 to 1, 0 to 2, and so on and so forth. These are the groups that you see here. They are numbered actually in the figure, which is small, and I'm sorry you cannot see it. And then you have non-conflict group set. You separate them so that you know these groups do not conflict, right? Because of their intent. So if I want to turn that way and this guy just turn that way, I can do them simultaneously. If this guy wants to straight and I want to go to, I can do this simultaneously. You have to understand that, right? And that's the advantage of the non-signaling intersection, because when you do signaling and go periodically, somebody may wait where he could go, but he cannot go because of the way the signaling works. I'm sure you have been in an intersection where it allows you only right turn. You want to go straight, there's nobody to interfere with you, but you cannot go because you don't get the green light. That's what you try to avoid here. You try to find the non-conflict groups based on the declared intent of the vehicle. Otherwise, I cannot do that. Then you decompose the problem, you can schedule the non-conflict groups, and you let them go. And then you change it again when the situation is. It's very common sense, I believe. So you compute the optimal velocities after that, and then you try to go as fast as possible, minimize the fuel, you have this trade-off, and then you ensure that the vehicle enters the section in the order that you have decided. That's all. This is a mixed integer quadratic problem again. We solve it pretty quickly, and it has this flow that you see here. Okay, so I compute the sequences, I can do the controllers, the low-level controllers, I do the non-conflict, and so on and so forth. All right. Ooh. Am I ready over time?
No? You're good.
Yeah. So that we see in our operation. I have a problem because my watch, despite the fact it's Rolex, it stops. That's why you see me all the time do this, okay? Because these are the ones that they actually get energy by moving them. So people think I'm crazy, but I'm not. I'm trying to make it get energy.
There are some watch movers. There are some watch movers.
Yeah, if I tell you how much they want to repair the watch, you better take it and say, okay, that's all enough, I don't want to do it. But here, the simulation works pretty well. All right, this is using simulation that many people use, and you have the optimal flow. It's not bad, it's not low, but you can see people here waiting. You see to find when they are going to be non-conflict and then go. Okay, this is totally unsignalized. Right? Okay. So, see. Come on. Yeah. This is a game opt. Sorry, let me go back. This is with the traffic light.
So the total flow.
This one with the traffic light. Okay. And this is with our algorithm. Okay. So this is a traffic light, and that's why you see this long queue waiting while you still go straight and you don't. As I said.
So the total flow is 8,000.
Yeah, vehicles per hour.
So around 2,000 vehicles per direction.
Yeah. And I think we've done some studies. And that's all game opt. And what we try to show here that we can handle different sizes of vehicles, like a bus or an ambulance or something else, getting the priority. Now, I don't know if you believe this thing or not. I'm very skeptical about this unsignalized intersection, especially if you have human drivers. Especially in some countries I won't name, but I don't know how well you can trust the humans obeying what you tell them to do, okay? That's another story. Anyway, we had a conference in Maryland, because we are close to the Federal Highway Administration and the Maryland Highway Administration. They gave us a 500 book with the preposterous title of what a good driver is. And I asked the lady who presented, I said, how do you enforce that? You tell me what I should do, but if I don't do it, how do you enforce it? Because if you don't enforce it, it's useless, right? Okay. But anyway, that's another story. They are interested in these things because the Maryland Highway Administration claims that they have very good instrumentation in many of these highways, which of course is the concept of these things, that I can get the information. Alright, so here is the results. Let's see. Here you have comparison of throughput between the traffic light is the red one, right? And then is the stop sign, and then this is the actuated traffic light here. Actuated traffic light. Okay, so starting I think with Praveen, they were doing wireless communications where actually a vehicle could communicate with the traffic light controller and say, I'm coming, and there are many people coming in my direction, and then give me more green. So you can adjust it with the green to avoid to have people waiting when they could go through. Okay, this is the adjusted traffic light concept. Okay.
You do that also with buses, bus priority.
Yes, yes, of course. In Germany, actually, in Germany and in Sweden, if you go to Kista in Stockholm, where Ericsson has a both experimental test bed, we can actually give you different priority for the bus lanes. Because the concept is we try to get the buses to come in the stop within plus or minus 2 minutes. Right? So I can get the pass, the car, then I have to stop everybody else. Not only the people here can go, but those people have to stop because the bus has to go across. Okay, so
Not everybody else, just those that are.
The competing.
That adds the conflicting groups, right? Because now I have to stop those that they go across because the bus has to go. Only for the period it takes the bus, and then I open it again. So this is the this is comparison of time to goal, okay, and this is comparison of fuel consumption. Okay, so we do pretty well for this. Of course, if we didn't do well, I will not show you. I'll be honest with you. But these are simulations. We have not gone to actual experiments. Okay, actually, one of the reasons we work with KTH is because there may be a chance that we can do this kind of experiments in about 10 square feet in Stockholm that we have this capability. Okay? Because in the group I work with at KTH, we have a smart mobility lab and we do many of these experiments. Okay? So, performance analysis, the relative performance increases with vehicle density again. Timed and actuated traffic lights provide similar performance. And we get 25% increase in throughput versus traffic lights, which is why you went to that. You want to avoid, as I said before, have people sitting over there where they could go and they cannot go because of the cycling of the traffic light. And then you have 70% increase in time to goal versus traffic lights and 50% decrease in fuel consumption. Okay, that's what our calculations show. We've done a lot of simulations. Right. And what else? When you have unbalanced, then you can get the performance is not affected by unbalanced flow. Okay, so if you put the throughput here, you get the various curves. The curve we have is the stop sign is the green, I believe. Okay, and then the comparison of time to goal is here. Again, we are pretty good on that. And then the comparison of fuel consumption is pretty good. Okay, unbalanced means that the traffics can be, you have heavy traffic here, low traffic here, so on and so forth. This adjusts automatically. Okay.
This is now also with human-driven vehicles.
Yeah, everything is here.
And do you have specific percentage or?
No, we have in the paper, like before, in terms of penetration, but not yet.
Have you tried going to even higher flows, like reaching the levels of levels that in the case of signalized junction, you will have queuing queues staying for more than a cycle, like saturated case?
Sometimes it happens, even with the experiments we have. You can see that the cycle doesn't empty of the queue. Okay, that's an additional problem that we try to avoid also with the traffic intersection. This also can be handled though by this adjusted light. Okay?
Yeah.
You don't have to go to non-signalized. You can say because I have traffic. Because one of the issues, I have worked with this many years before. I don't know if you remember the just actually the award we got from our traffic control paper with Bill Levine was because we were the first to adapt queue management, where we showed that we don't need to actually calculate every time it comes in. Once you have the statistics, you do the so-called UC rule. Remember, it was before, and then Praveen and Jan did this for networks. Okay, where you create what's called the Giddings index. You create priority indices based on the data, and then you give as long as the queue is not empty, you keep priority that way. And that you can adjust now more to avoid the problem that you have heavy traffic here and less traffic here. Because the new and C are
The max and the algorithm,
Max pressure.
max pressure.
Yeah. And and you can do all kinds of bandit algorithms there where you adjust this in the adjusted intersection. The problem is the signal, it has to come there in time, right?
Yeah. My question was really whether when you try to go to higher flows, whether you keep on achieving the same kind of efficiency improvement.
Yes, with our algorithms, not with the traffic light. With the traffic light, you're going to create what you mentioned, that is going to be people waiting. This is large scale signalized multi-intersection control, where, as you know, what you're trying to do is create so-called green wave, right? I'm trying to get you not to stop. And that we learned first many, many years ago when we looked at the traffic control of Sydney. There was a brilliant traffic engineer there that they had a very peculiar traffic. In the morning when everybody goes to work, there's several houses where they have a lot of traffic and very little that day, and they create green wave. Okay? So that of course makes assumption about velocity and how you take that everybody behaves okay with respect to velocity, and you try to keep that. Because if you start stopping, then you create all kinds of problems, both for this flow and for the others. Okay? So that's what we try to do here. These are connected intersections, means the intersections communicate and they inform each other how well they are meeting, okay, the specification in the task execution, which means emptying the road, okay, so you can push the traffic. Alright, so you get again mixed traffic. Alright, they are not direct controlled, but they are affected by the traffic rules. The traffic lights model is finite state machines, okay, and the output, the velocity, and large change control for this traffic light and so on. Okay. Alright, so
The connected intersections have to be close to each other, or you can think of a highway with two exits?
You have to estimate the distance, the velocity you're going to give them, and how uniform people follow the velocity. Because you have to estimate the expected time and the variance. Again, the variance is a risk given to the introductory comments I gave you, and if you do risk sensitive or robust control, you will do better because you'll be able to adjust the variations. Okay? Right. But this may force you, if you have intersections with lights, to also adjust the light almost every time horizon, okay? To accommodate that you don't create a stop. Because of if the variance is very high, you may have to extend the big flow more than you want. Okay? All right, so the formulations here is like that. I have traffic lights are formulated. This is not unsignalized. These are traffic lights. I'm trying to create three waves. So you have state machines. Switching between safe states and not safe states, okay? And then I group them to create a green wave. And then you do the lane changing control so that you can put them over there. These are various times, and these are, the minimum is the various times, and so on and so forth. You can study those. There's a variable that mathematics that go under the name of partial semi-rings. I'm not going to go over here. And you get this centralized controller. Right, like that. The objective function is again mixed in the linear programming, and you maximize the driver distance for each vehicle, and the constraints are vehicle dynamics, lane changing, collision avoidance, and so on and so forth. Now, there are famous mathematics that people have used for trying to model this kind of problems, which are go under the name of partial algorithmic semi-rings. The one you may have heard is max plus algebra, which can be used for both for traffic and for manufacturing. So these are linear systems, but we put quote unquote around them because they are linear, but the underlying arithmetic is not linear. Okay? It's not sum and product like we know the numbers. The one you have maximum. Okay. And everything you know from linear systems gets generalized. Controllability, optimization, and so on and so forth, except you have to do the calculation this way. The friends, okay? In your people did a lot of work on that. There are books, there's free software you can get, and you can use it for these problems. I'm telling you that because the latest development we have, we actually now have hardware that they can do the maximum operation real time, free of charge. So then it becomes extremely fast. When you do numerical analysis of the speed of an algorithm, you try to find if one of the operations, you can usually have two operations, can be done by hardware instantly. Okay, so if in regular arithmetic, we pay attention to multiplication because addition is trivial. Okay, so multiplication is more expensive. So again, we try to find out if there is one operation, and I found a group of lists that they have this max operation in particular hardware that does it in real time. And we're actually working with them, trying to see if some of this can be used to hardware that we put into the controllers to give this even faster. Okay? Again, the problem is you want to do these things fast. As fast as you can, the better you can, the better you perform. Okay. all right. So the decentralized controller, that was centralized and decentralized. You have CAPs within a range of a single intersection, the question you were asking me, along with the corresponding traffic lights. So you now group according to distance, if you like, the UAVs. And then you have control handed back to the CAV outside the individual control zones. And you get now several smaller mixed integer program problems that you can solve faster. And then now you have the problem of you don't know the whole picture. You only know your local environment. And you do sort of local optimization and you hope that you can patch them together and everything will work. Okay? Again, in the name of speed. Okay? So you can do this real-time operation fast enough for these things to work. And you can do hierarchical traffic control where you have a supervisor which gives guidance to these groups that you created, and then which is not again unheard of. But in each intersection you have an IDC as in centralized, and then you use probabilities how well you do for each intersection, and you do performance with these methods that we have, which are comparable to centralized. The best way to centralize is how close you come to centralized, okay? Because basically now you have less information, and we've been able to do that, and that's, I think, the results here. I don't know. Is the movie here or not? Yeah, there is. I don't know if you see the thing running. The little things that look like ants. You see the little things that go at all? They move here. And these are the cars that go to these intersections and so on and so forth. And these are some statistics about how well you perform on different methods which you can look at. Okay. The next problem was software mitigation. Okay. So there's a fluid dynamic model of congestion that says creates some congestion, and there's a wave propagating backwards, which is the software. This is old story. Okay. So and these are sort of the macroscopic model of traffic, and analyzing the soft waves and try to understand how you stop it. So the new idea that we have studied is I can now put autonomous vehicles, right? There's a famous ring in California that they do these experiments, mathematics people, control people. The problem with this particular scenario is there's a one lane, and they go around, which is not a real problem, right? Because you want to go into a multi-lane highway and see you can do there putting the autonomous vehicle so you can stop the creation and therefore destroy the creation of the subway. Right? If you have one dimensional problem, it's easier. If you have multi-dimensional, actually you can do better because you can actually put in different places the autonomous vehicles and try to control the subway. Right? There's a lot of literature on that, and there's actually this ring, which is the actual ring, that people do actual experiments. And you can do also similar experiments in the test bed we have in the University of Michigan, which is called something city, okay? And you know that case. All right, so we studied multi-plane highway with the same problem, the placement of the CAVs, okay? So how many CAVs you have, what is the speed limit, the number of lanes, and the length of the loop, okay? So again, the idea is you're going to put CAVs, which are your agents, to try to prevent the congestion by controlling the velocity. So it's extremely important to understand where you place them to have this effective situation, because you try to avoid the initial stops, and then therefore there's no software. Okay? So, and we don't do that by fluid dynamics. We use the microscopic model, if you like. Okay? So you have from the data that you get, the information, you create traffic state estimation, various ones, right? Then you get vehicle-to-vehicle communication. Then you detect that there is congestion going on in different parts of the lanes. Then you control the computation of where you're going to put the CAVs and what velocity you're going to give and try to stop this down. And then you implement the controllers and you hope that you succeeded in not creating a shockwave.
What do you mean where to
Yeah,
put the
exactly.
CAV?
Huh?
What do you mean where to put the CAV? Which
Suppose you have 5 CAVs, okay?
Yeah,
Well,
but
five
they are
CAVs.
where they are. You cannot just place them somewhere.
You can move them. If you have multi-lane highway, you can move them ahead or different lanes and so on.
Okay, limits.
Yeah, of course. But you don't put them in a lane like that because then you don't help the other lanes. Okay?
Okay. Lane-wise, yeah. Okay.
Location.
Yeah, location you cannot really affect it because
If you have heavy traffic, if you pass a condition, forget it. Yeah, you're right. There are limits. Okay? So first you estimate the traffic, right? So the estimation is based on something, almost an empirical distribution of velocities, computation based on memory of all surrounding vehicles. Okay? So you look around you. But remember, we're talking about vehicles that communicate with each other. One form of communication is sensing. If you play team sports, you don't call each other on the phone and say, give me the ball here. The way you move, there's a meaning. Whether you play soccer or basketball, or you put your hand behind, you ball, and this gives you signaling, right? So sensing is a form of communication. We call it indirect communication. And you have also signal. You use that to try to get some estimate, okay, of the state of the traffic locally. Okay? Then you detect the shockwave. Okay, shockwaves are characterized by a sudden change in the traffic state of highway. All of a sudden, the velocity starts slowing. We're talking about highway. The highway is supposed to go with certain velocity unless you have an accident. When you start detecting changes, that says, wait a minute, there may be here something funny. And then you have to use the communication oriented between the vehicle because you cannot inform everybody. And that's taken into account here. You compute the worst case traffic. Again, you may criticize this as conservative. You compute the relative condition in the worst case. And then the shockwave detected in the relative condition is a threshold condition. And then you have to actually see what you're going to do. You control the shockwave dissipation. Okay? So you have the CAVs as a moving bottleneck. I'm trying to break it slowly, not abruptly, so that I can prevent congestion. I don't want to create bumper-to-bumper static vehicles. That's the beginning of the shockwave, if I get backwards. Okay? So the control is a function of the worst case traffic condition that we estimated, the distance to the worst case, and you of course would have to take into consideration safety and various parameters we have here. Alright? So this is the curve you get. What you have with these are these parameters of different values, and you can see what you get. Right? This is hard brake and smoother, if you like, brake, and this is how you adjust the velocity between these conditions. Okay. All handcrafted, believe me or not. And you have lane change controller. You can actually, what you were talking about before, you can distribute the CAV somewhat uniformly and try to avoid congestion by people. You've seen many times. Okay, this lane gets congested and then everybody moves to the same lane at the same time and now everything gets congested. So they get here's constraints. You can do that. See, I don't know, you can see the movies? Yeah. So this is with no control. And you start seeing you see here, they get bumped up. And here with the same traffic, you don't get this. This is the shockwave here. You see propagate backwards? How many times you've seen that? Okay? And here it does. That's the end of this story. And here we looked at the question you were asking before, Marcus, as far as you know, we're going to see the penetration. And you can see that this is anticipated within 5 minutes. The choice of this controls it. Here, this is the performance. Okay, that you get. You don't get this chaotic stuff and so on and so forth. You distribute the shockwave if you have the CAVs. This is the CAV penetration of 7.5%. I think we have more. And of course, if you have more, you can do better. Okay? And we have learning about I'm going to skip the rest because I want to go to the second part and I'm already more than half an hour. Okay? So the rest, here is the proposed method performance if you do deep reinforcement learning, as long as you do it fast enough to adjust these things and combine model-based and data-driven methods, which is what we advocate for this program. Skip that we have studied the effects of vehicle-to-vehicle communication via infrastructure. The only thing I want to tell you is that when we deal with multi-agent systems, we don't use one method, which is 99% control literature, because in multi-agent systems, you have to consider the collaboration network, who collaborates with who communicates with whom, and who shares information with whom. So we treat at least 3 graphs, or multi-graphs as they call it, because you may have more than one connection between nodes. And these functions, they don't coincide on every node. And we've done enormous amount of work in this area, all kinds of multi-agent autonomous systems. And the most important research area results we get is on the impact of one topology on the other. For instance, if you want to have fast convergence up here, whether it is opinion dynamics or social network or traffic control, what is the communication topology that gives you the fastest speed of convergence? Okay, so we've been able to, first of all, prove that on simple networks, small world graphs have that property. But we proved it not by simulation, by using some stochastic methods. And then we went to something that's called expander graphs, which came from information theory, which in plain language means locally rich, globally sparse, because this reflects immediately communication cost, and we showed that the optimal communication you want to have is expander graphs, and the problem that we're studying now is how you can dynamically maintain the topology of the expander graph. Okay? And we try to do that by solving the problem of topology control as a variational problem. What is the cost of communication that if you optimize, the answer is an expander graph? We have not been able to solve this completely. I don't think it's possible. We have come close to epsilon expander graphs. So expander graphs were introduced in information theory for coding, okay, by a famous Russian information theory by the name of Pinsker, who called them magic graphs. They play an important role in coding. For instance, in MDPC coding, if you know the terms, even Gallagher in his thesis used it. Then the information theorists abandoned it, and mathematicians took it over. It is for advanced study in Princeton. They proved very nice properties for expander graphs like fast diffusion, very fast caching, and all that stuff, which is useful for control. And that's how we run with them. And they are the proper extension of small world graphs and general graphs. Okay? So that's what I'm going to say here. And there's a lot more work.
You are running belief propagation algorithms. I didn't get it. Because LTPC the coding is based on belief propagation. Okay.
But that's the application of expander graph to LTPC. That's not what we do. We use them because these are the best communication efficiency for trying to have the agents get the information they need to work. Okay?
Okay.
Right? So, for instance, there's a famous problem in control theory that says that platoons is unstable.
That?
Platooning is unstable. How many papers you can find in that? Google it. Hundreds. And the fundamental mistake they make is that in wireless communication, they assume only near neighbor communication. Tell me how you're going to do that in wireless communication. How do you constrain communication to be only nearest neighbor? There's a way of doing it. Okay? Alright, so by modifying slightly, by allowing neighbor communication, which is very natural, it's solved. You can show that you can actually the platooning problem is stable. I give you the practical example. You drive. You don't want just the car in front of you. You want to know what the car in front of you. What the car in front of you know. If the truck comes in front of you, what do? You stay back. Okay? Because now you cannot predict what's going to happen. So this is exactly a practical manifestation of what we're saying. Assuming that the only thing is near neighbor communication is wrong.
Okay.
The same way it's wrong to assume links in wireless communication. There's no link in wireless communication. There's a wave. The only way you have a link as an abstraction of wireless communication is because the packets that I know addressed for you drop it. That's a simple thing, but you forget about it. Anyway. So, this problem I'll tell you more about that. This is the problem of bidirectional overtaking, whether you do it collaboratively or not. And that's where the most important variable is your ability to estimate how cooperative is the vehicle you're passing, how many times you go, especially in Greece. Okay, you try to go to rural highways, you try to pass, and the guy who's coming the other way starts blinking the lights, try to drive if he's not cooperative. Right, so we'll go to this in the next part. So So that's what we did here. It's a summary of what we did, and then the papers are listed on here. These are things that we're trying to do now. And the paper right here, I can send it to you. And there's even a chapter on one of these traffic books that we did. So now I go to the second part of the talk, which is basically
John, I think we're running out of time. How long is that going to be? Oh,
what time we start? 10:30?
Yes,
That-
Okay, so I'll summarize it in, give me 5 minutes. Right. So the problem is safety, right, in these vehicles. That's basically the hardware that we use, the flow, that we're trying to solve these kind of problems. Multi-lane highway, we try to avoid the problems of that coming in. Okay, bidirectional overtaking, and the problem you have sometimes somebody's parked on the shoulder and you want to avoid that. Okay, so this problem we work a lot with Honda Research Institute. Okay, so these are the kinds of problems we want to study. Okay, so I'll go to some of the important things here. You can look at the rest of them. Okay, so I looked at the bidirectional highway. Okay, so basically the problem is I want to pass a car. And I want to try to have human-driven vehicles, and I want to estimate the distance between the vehicles and their velocity and their variances. You can do all that. The bad news is that the most critical variable is the ability to estimate the cooperative use or not to track the driver you try to pass. We've done this formal method with control and with this. Okay? Right, there's all kinds of issues here in terms of the models. These are the symbol as far as the motion and the sensing. So you basically you try to execute this maneuver. There are different difficulties of this problem where you start and you can go back if you have space. Or once you start, you have no option. You try to calculate the probability of hitting or not hitting somebody at the other end. Okay? You study this, and we have all kinds of nice algorithms. I'm sorry for that, because so we use mixed index there, model predictive control for that, with different criteria to solve it. Okay? You can read the papers. And we've been able to do it. Let me see this place. Not that I'm trying to impress you with it, but actually. Anyway, the issue here is that the most critical variable for the success of that, in all kinds of difficulty, even if you go halfway and you have to back off, is whether the two drivers, the one you pass and the guy comes from the other side, is cooperative or not. It is common sense. If you drive in rural highways and you try to do this maneuver, this is your fear all the time, right? When I was coming this morning from Iraq with the taxi, that's what the driver was watching, especially in some famous turns around this road, that you have the road accidents, okay? Anyway, yeah, see. Anyway, so we've been able to do that under very difficult conditions. These are some parameters. Now, cooperative is when vehicle cooperate. The driver slows down, allows you to pass, he doesn't try to accelerate because he doesn't want, he or she does not want to pass. You've seen the situation. He doesn't blink the lights, the other guy, when you try to pass, try to push you out of the street. Anyway, that's one problem. In this second part, I'm sorry for trying to compress two talks in one. This is multi-lane highway where we have our best results, where you're trying to, these are actual videos from Honda, and you will see somebody sneaking in. Then you have to know how you avoid it, because you don't want to hit your brake. You're trying to avoid try to estimate how aggressive the driver is to the limit time you have, and try to allow more tolerance. This is exactly robust risk-taking control application. I want to show you that because this is something we spend a lot of time to understand. So here's the situation. How much tolerance I need to allow for people to jump. Okay, so the issue is the robustness of the control algorithm. We have shown when we know the models, the work that we did in the late 90s, we extended completely the infinity theory of John Doyle and Keith Glover and Francis and all that to fully nonlinear systems, set value systems, and automata, and the solution is the same. It is two Hamilton-Jacobi-Berman equations, dynamic programming equations, one online that tries to estimate the information state, meaning statistically unique for control, and the other one offline that gives you the controller as a memoryless function of the information state. The term information state is due to variable. I learned it from him when I visited was writing a book with Kumar at the same time, and one of the things we all agreed is that if you study any stochastic control problem, the first thing you have to understand is what is the information state. In a computer science sense, meaning that the controller now has to be a memoryless function of the information state, otherwise you don't have the right to call it state. Okay? So in this case, we did it, and these two Bellman equations, if you like, explain why in the linear case you get two Crete equations, not one, two. The first guy who did that was my first advisor at Harvard, David Jacobson, who, out of mathematical curiosity, showed that if you solve a linear problem where the criteria is an exponential of an integral quadratic, again you can solve it by solving a Crete equation and linear feedback control. This was a mystery because it was just computational. And 10 years later, Jason Spire did the same thing with partially observed, 10 years. And then 10 years later, Doyle and the others, Kip Glover and Bruce Francis, Carbonell came up with, especially John in the beginning when he was with Honeywell, said they listen, control people, everything you do is not robust. This was serious because they came from Honeywell designing with Winterstein autopilots, and they were putting them into these models, and they were not robust. Not robust means small perturbation and the system goes out. We don't want that. Okay? And they had the solution to the Crete equation, no system theoretic interpretation. Just so happened that the solution has two Crete equations. With Matthew James and Ital Patel, when we did the robust control problem, there's another talk that I gave yesterday to the University of Crete, I can send you that. We saw this solution that is the two Bellman equations. And this showed that you try to estimate the cost to go. The information state has the interpretation of cost to go, which is interpreted as risk, right? You try to estimate how well you're going to achieve what you estimate is your cost to go. And that's risk. There's no separation theorem in robust control. You cannot estimate just the condition distribution of the state and make the control the condition. That's not enough. You have to give an estimate of the risk. Okay. All right, so that's what we do. Exactly. This is the thing. We try to find out how much you can sense, how much tolerance you can allow, and believe it or not, with this criteria, I'll come directly to the meat of it. Here is a movie of one algorithm that it has problems. I'll skip it because Marcus is going through my other room. Then we extended, these are previous work, they have problems. Okay, then our algorithm, when we did this robust control, worked pretty well. But here is the important new thing, which is this risk-sensitive control. We showed that to get robustness, the three problems, so robust output flow control, the game theory problem, where nature fixes the disturbance and picks the controller to take the minimum effect of the disturbance, and the risk-sensitive control, where you minimize an exponential integration, they're completely equivalent. They all have the same solution. Okay? Mathematical solution. It's a zero rate. This is true when you have the models. If you don't have the models, in the talk I gave to MIT in 98, and I said, you have to do learning. And what's the obvious thing to do? Okay, we have two dynamic programming algorithms. Make them approximate dynamic programming. Meaning two learning. Now, the middle perspectives, if you look at this wonderful new book, it says what we learn from AlphaGo, and he actually explains that what they did is the same thing. They did a rollout real-time dynamic programming algorithm and an offline dynamic programming algorithm. And we try to prove that this is exactly what we say needs to be done. The engineers did it intuitively, and we say this happens because you're going to have robustness. And when you play this thing, you make the rubric cube and so on and so forth. Okay? Look at that. There's also a lecture on that. Just the advertisement of something that's quite exciting. Here, in this work, let me go to the criteria and stop. Okay? Here's the condition value at risk. Okay? Condition value at risk means, in practice, that I'm trying to estimate the tail of the distribution that I'm going to do the bad thing. I'm going to sneak into your lane. And if I estimate that, I can now allow more distance so that I am ready when you try to do that. Okay? So you use this condition of variance at risk as one of the metrics, the other is performance. And that's why I told you in the beginning that you need duality between a performance and risk. Why? Because if you have rigorous duality, you have a rigorous and precise definition of what a Lagrange multiplier is. Remember your first class in optimization, you learn that the Lagrange multiplier is a derivative of the optimal value with respect to the right-hand value of the constraints, right? If you remember that I told you I can change the constraints to metrics, you can also interpret that as a derivative of one metric with respect to other. And that's not something you throw there and try to find randomly what lambda should be. It has a definition, it has a precise definition of sensitivity, which tells you if you want to be high performance, meaning go fast from here to there, you have to take risk, you may crash somebody. If you want to make an aircraft safe, you make it heavy, but then slow. If you want to make a car safe, you make it slow and heavy. So there's the obvious trade-off. So to us, was not surprised, the mathematics came from mathematics of finance, because there they care a lot about this distance. Okay, anyway. So this is an application of that to a traffic problem with contact. We did it, here's the algorithm. No, not this one. Not this one. Come on. This one. If you place, you will see that. Come on. Yeah. You see, it goes like this, and this carries a distance, and it doesn't. It tolerates it. Okay? In different manners. So the application of this idea is to track. Let me stop here and take at least a little bit of time. I won't go to this. You will see in the talk. Okay. Sorry about this. As interesting ideas here about potential, you want to start again other algorithms. Okay. The interesting thing here is that these algorithms were tested not only by simulation, but the actual secret simulation that Honda has. That is, they believe it's almost exactly what happened in their test bed. So when they say that in our simulation this passes, it means we have high confidence that if we go and visit the test bed with real cars, we're going to work like that. That's what was exciting. I'll stop here to have a little bit of questions. Thank you very much. You will get a lecture, and so you will be able to. Here's my coordinates. I'm not trying to hide. You can find me. You can ask questions. You will do.
So questions, Mark?
Yeah.
Thank you very much for a very exciting presentation. Very glad I didn't know several of these works. So I'm glad that you are so much into autonomous vehicles also. I mean, cars and traffic. Just a couple of questions. We did also some work in the first ERC advanced grant in automated merging.
Yes.
But we didn't address really the problem of sequence. Just for a given sequence, the problem of merging. And that was also because we experimented with different simple policies like first in, first out, or similar, reasonable heuristic sequences, and found out that there was not much difference in the final performance. So I wanted to ask, what is your experience? I mean, if you take something heuristic that is reasonable to find the sequence, do you see big differences?
I don't think heuristic is going to give better results than this.
Better? For sure not, but whether there are big differences if you take the optimum sequence.
There are big 50%, 45%.
How much?
40%, 50%.
40%.
Yeah. In terms of throughput and the various metrics, timing, energy efficiency, and so forth. We beat the Google pattern by a lot. Because the Google pattern is all, even the fact that it's all for autonomous cars, right? Our problem is more difficult, because you have to deal with humans. So why it's difficult with humans is because you have to deal with uncertainty that you don't know.
Yeah, of course,
that's the problem, right? Humans are non-causal systems. You don't know what I'm going to do. I can jump right there and start dancing next time. You don't know that. I'm not a causal system. Knowing my past history, you cannot predict what I'm going to do in the next few seconds, right?
Sure.
So there's a big mistake that a lot of people use causal models for humans. That's wrong. So the biggest problem with this mixed traffic is how well you get some estimate with changes of the behavior of the humans. And the book I told you, the 500 book about good drivers, addresses this. And the question is again, so I can measure what kind of driver you are. If I want to fix you, mean maybe you're a good driver, how do I do that? What do I do? Take your car away, or we are on the highway on drive? Okay. Here we're trying to say no. I try to estimate how bad you are and take my measures, meaning what distance, and so forth.
Also, we started doing some work. We just produced the first publications on signal-free crossing. The point is that we use lane-free. I mean, we don't have prescribed paths for crossing. So that gives you more flexibility,
Yes.
you know,
And more risk.
and I'm not sure more risk, because if you have more flexibility, you may have also.
You still have to give some tubes and figure out that they're not going to hit each other, right? At some time horizon.
I mean, if you optimize if you want to optimize jointly for all people simultaneously.
But you cannot assume that the car is going to run like that in a nanosecond.
No, but you give constraints.
Yeah. If you put constraints, you're actually saying that the path.
So anyhow, of course, there are different problems, but I'm just saying that there is also the possibility to cross signal-free, but without specifying the paths. That's why I asked you the question. In which case, you don't need to consider specific conflicts. You avoid using Boolean variables.
Here's my answer. You're not going to gain anything by that with performance. You can see that if it happens. Because, first of all these problems were scrutinized by GM, Ford, and Honda, as far as how realistic they are and how they see it. I'm not going to try to defend them, I'm telling you that was how we think. We go and ask what is the real situation, what is the real problem, how we can solve it. Now, I will look at what you say and see if we can actually do anything, or gain anything, or whether it's a plus or minus when we don't allow, we don't need this conflict groups and so on. That's an interesting point. Thank you for making it. Yes. You have a question?
Yeah, so thank you very much for the interesting presentation. At some point you were explaining about the intersections, and you mentioned that you looked at them both with centralized controller, decentralized, and hierarchical.
Yeah.
So I'm kind of curious about the performance between the centralized case and decentralized.
Okay, centralized means you have a traffic control management center, like you have in many cities. If you have it in Athens, I don't know if you have it here, you can see the entire network. You can give centralized commands. Decentralized means that's too slow, often, and I try to do local control and try to give more accurate control with centralized. Okay? What we've showed is that, at least in the forums we looked, and the particular topologies of intersections because this matters, we were coming with the decentralized algorithm very close to the centralized.
Oh.
Very close. At least in the experimental view, which is the best you can hope for. The requirement though for that is that there is some exchange of information between the local controllers, meaning that there is vehicle to infrastructure communication. You cannot get something similar to that, right? The teachers and engineers tell you that you cannot get something out of nothing. Okay? There has to be a cost for something. Yes.
Thank you for the interesting talk as well. I have a question regarding the no signal intersection approach. So this was applied in mixed traffic, correct? So we have this approach that we can understand with the auction within the system, but how does the human driver know the auction that is taking place and know when to speed up or slow down? How does the human driver know when to pass through the...
I'm assuming vehicle infrastructure communication, so I tell you. So same way I tell an aircraft, you now.
Have an onboard.
It comes to your board.
It has an onboard communication, so
Yeah.
they get the speed that they have.
I'm assuming vehicle-to-vehicle communication, vehicle infrastructure communication, including signals. Okay? So the best example I can give of that is you are in an airport, there is a controller that tells you now you take off, the other one is landing, you wait, and so forth.
More questions?
Okay? Thank you very much for coming.
Thank you. Thank you very much.